bars. Okay, notes 5, sampling distribution of a difference in sample means. So it says, why do we have this? So this is a common practice in statistical inference. We're going to start talking about statistical inference when we get to Unit 6 and then finish out the course in Unit 9. Remember, we look at 2 samples from 2 populations and see if there's a significant difference. This is true for sample means and sample proportions. Or if we're not looking at samples and we're looking at experiments, this would be us looking at 2 experimental treatments to see if there's a difference due to natural variation or the treatments. So 2 experimental treatments, difference due to natural variation or the treatment. And we'll continue to do more of these problems in upcoming units. So this next part here where it says recall, this is all 5.4. So this entire section here is just a brief recap of 5.4. Okay. And in 5.4, we got introduced to new variables and the significance of those variables. Because for sampling proportion, we were dealing with p hat and p1, p2 for the differences. For sample mean, we find out that we have different parameters, mu and sigma, and that we also have different formulas for the spread or the standard deviation. So recall that we still want the shape to be approximately normal. That is always the goal. No matter which distribution or sampling distribution we're working with, we always want approximately normal because that's going to be the easiest one to find our data for using that normal distribution on Desmos. Okay, this is going to be true as long as what condition is met, because this condition changed in the last notes. So instead of large counts condition, we're using the central limit theorem. So we can assume that it's approximately normal if n is less than 30. So then we assume, okay, it's normal. Or if n is greater than or equal to 30 by the central limit theorem, or you can abbreviate CLT, then we assume that it follows a normal or a approximately normal distribution. So if it's less than 30, we don't care, we assume it's normal. If it's greater than or equal to 30, then we have to say by the central limit theorem. Do not make the mistake of saying by the large counts condition, because you will get it marked wrong since large counts condition is only for proportions. Central limit theorem is for means. Okay? We also know that the center, mu of x bar, is equal to mu. Okay, so this didn't change too much from proportions. We just use x bar instead of p hat. And then we know that this is true, or this is a good unbiased estimator as long as our samples are random. So either randomly selected or randomly assigned in an experiment. Okay, and again, we want this because we want mu to be an unbiased estimator. Why is that important? Why would we want it to be an unbiased estimator? What happens to our data if we introduce bias? It does what? Say that again? It skews, it could alter, it changes. That could be for good or for bad, right? But it doesn't give us an accurate depiction of what the data represents. So we want this to be random, so our mu is unbiased. Okay, and then last we have spread. So this is where standard deviation formula changed. And it was sigma of x bar is equal to sigma divided by the square root of n. Notice we have two different types of sigma, two different types of mu. This mu and this sigma are going to be given to us in the problem. Okay, so both of these are given. Okay, it's different than our estimators for our distribution of mu of x bar, sigma of x bar. Okay, these can change based on other conditions that we're putting towards our problem. And then we know that standard deviation formula is true as long as what condition is satisfied? This one didn't change from proportion. The 10% condition. And remember, that is that the sample size has to be less than or equal to 10% of the population size. Okay, so this was pretty much a recap of 5.4. And then, of course, after you went through all of this, you talked about how proportions or sampling distributions of sample proportions are used for categorical data. And sampling distributions of sample means is used for what? Proportions was for categorical. Mean is for quantitative. Okay, so now we're looking at 5.5 notes now, and that's the difference. This is real quick notes. We're going to go through what these new formulas look like, and then we're going to do one example problem. So for a sampling distribution of x1 bar minus x2 bar, we can label x1 bar to be the sample mean for the first group, and x2 bar to be the sample mean for the second group. Okay. You'll notice that shape, center, and spread are going to be using the same exact conditions to prove. We just have to make sure that each of the samples are going to satisfy each of those conditions. So it's not enough just for one sample. Both samples would have to meet them. So we're still assuming approximately normal. Okay. We are still using mu for our center. So this is mu of x1 bar is equal to mu 1. And mu x2 bar is equal to mu 2. Which means mu of x1 bar minus x2 bar is equal to what? Mu 1 minus mu 2. And then for standard deviation, we had our new formula above. That was sigma of x1 bar is equal to sigma 1 divided by the square root of n1. So this is talking about sample 1 from the first group. And then sigma x2 bar is equal to sigma 2 divided by the square root of n2. Okay, so this is the standard deviation from that second group. And since we're subtracting them because we're finding the difference, we know that standard deviation and variance doesn't matter if it's subtracting or adding. We're always going to do what? It's going to be the same thing we did with proportions. Adding or subtracting variances is the same as just doing addition, right? Adding or subtracting is the same as just doing adding. So remember when we did those combining random variables and we were testing out the different standard deviations if we were adding or subtracting? We found out that no matter what, it was going to be the same formula. That's what you guys did on that 5.1 homework. Well, here we know that it's going to be that same. We're just adding them together. So sigma of x1 bar minus x2 bar is equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And we get to this formula the same way we got to the proportions one. So we first would actually plug this in to the standard deviation formula that says we take the first sample and square it, plus the second sample and square it. But when we simplify that, the radicals that were attached to the sample sizes went away. So we're just left with this formula. What's nice is that these formulas here are on the formula chart. So if you go to the formula chart and you have sample distributions for proportions, so all the formula for proportions are here, and then right below it is sampling distribution for means. All the formula for means are here. Okay, and then even when we talk about standard error later. So you don't need to memorize any of these formulas. The only one that I would memorize is the conditions. So the formulas for like 10% condition, large counts condition, and central limit theorem, because those are not on the formula chart. Okay. And of course, with each of these, we had to meet the individual conditions. So for approximately normal, we can say that this is going to be true as long as N1 is less than 30 and N2 is less than 30, then it's going to be approximately normal. Or if N1 is greater than or equal to 30 and N2 is greater than or equal to 30, then by the central limit theorem, we assume that it's approximately normal. Notice that these are not a mix and match thing. We're not saying if sample 1 is less than 30, but sample 2 is greater than or equal to 30, then we can assume approximately normal. That would not be the case. You don't typically see this in this beginner course, but if you did ever see it, you don't stop the problem, okay? You would just say in your conclusion that we need to be cautious of our answer because we couldn't assume approximately normal. Okay, so we would just add that sentence to our conclusion and that would be good enough. Okay, it's not something that has to completely alter the problem. We would just keep on going. But again, that's more like in the next stats course if you choose to take that. Okay, so for mu, in order for it to be an unbiased estimator, we know that both of the samples have to be what? Random. And that means randomly selected if it's a sample or randomly assigned if it's an experiment. And then lastly, standard deviation. We can only use this equation for the standard deviation as long as which condition is met? 10%. And the 10% condition is used to prove what? Besides that we can use standard deviation formula. Starts with an I. Independence. Okay, I would put that in there so you don't forget that we are using this to prove independence as well. And remember that the 10% condition says that the sample has to be less than or equal to 10% of the population, which means this has to be true for both. So N1 is less than or equal to 10% of population 1, and N2 is less than or equal to 10% of population 2. So again, I would memorize these formulas that are part of the conditions because you will not get that on the formula chart. Okay, and then we're given one example here, and for this example, I suggest either getting 2 highlighters, right, or underlining and boxing the 2 different averages that we are going to compare here. So it says, a study is conducted to compare the effectiveness of 2 study techniques, A and B, in improving the test scores. For technique A random sample of 80 students yields an average score of 85 with a standard deviation of 10. That whole sentence is telling us everything we need to know about that first sample. So technique A, random sample of 80 students, average score of 85, and a standard deviation of 10. So that gives us our sample size N, our average or mu, our mean, and then our standard deviation or sigma. And then the next sentence says for technique B, a random sample of 100 students yields an average score of 82 with a standard deviation of 8. Okay, so that is our other sample. Okay. Then it says calculate the probability that the difference in the average. So I'm going to box this, difference in the average. Because those words right there tell us that we are doing a sampling distribution of a difference in sample means. Okay? The word difference and average tells us a difference in sampling means. Okay? If we did not see the word difference, then we would just be doing a sampling distribution of sample mean. If we did not see the word average, then we know we're talking about a difference in proportions. Okay, they have to say average or mean in order to be a sampling mean. Okay, between technique A minus technique B, so this is what we're trying to find, is greater than 4. So in order to solve these types of problems, I have to remember my 4 C's. And what is my first one? Communicate. Okay, so for communicate, I need to list what my 2 averages are. So I have the average for technique A and the average for technique B. So you could say mu of 1, or we're just going to say mu of A because it's technique A. So mu of A is the mean score of students using technique A. And then mu of B is going to be the same thing but using technique B. Okay. Once we label this, and this is the same process we did for proportions, we said P1 is equal to the proportion of this. P2 is equal to the proportion of this. Okay. Then we have to label what we're trying to find. Well, we're trying to find the probability that mu of x bar A minus mu of x bar B is what? Greater than 4. Okay. That's it. We're done with communicate. What's the next C? Creates. And I'm going to give you another word that could help, and that's conditions. So they use create because create can be used for a lot of different types of problems. But notice in these sampling distribution problems, we're always trying to prove the 3 conditions: random, independence, and normal. So you could use the word create or conditions for your second C. So first we're going to prove random. So we look in the problem, and do they mention anything about them being random samples? So we would say both are random samples. Okay. This is important because we can then assume what is going to be our unbiased estimator. So go back to the table above where we said this is only true if this is going to be random. And what is above that? The center. So this is helping us find mu. Okay, so because of this, we can say that mu of x bar A minus mu of x bar B is equal to mu of A minus mu of B, which is, what 2 numbers are we subtracting? 85 minus 82, and that gives us 3. So we just found our new mu value based off of the difference between the two averages. Okay, that's important because we're going to use that mu value in our normal distribution on Desmos. Okay, the next one is independence. For independence, we use which condition? 10% condition, and we have to prove it for both. So we look at the very first one, and that is for technique A. What was our sample size? 80. So we have 80 is less than or equal to 10% of, and do they give us our population for technique A? No, so what do we have to do instead? If they don't give us a number, we have to write it in words. We have to write it in words. Okay, and those words are all students using technique A. So this could be all students at the school, all students in the United States, all students in the world. Okay, all students using technique A. Okay, would you say that's a safe assumption? Yep, so we'd put a check mark. Okay, what is the next sample size? 100. So we say 100 is less than or equal to 10% of what?
All students using technique B.
All students using technique B, which is again a safe assumption. Typically, they're not going to give you the population size. You're always going to have to write it in words. Okay, so now that we just proved independence by the 10% condition, we can now find what parameter? We already found mu, so we need to find standard deviation. So we know that standard deviation of x bar A minus x bar B is equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So this would be equal to the square root of what would be our first fraction. 10 squared over 80 plus, what's our next one? 8 squared over 100. I wouldn't bother simplifying this, just plug it straight into Desmos, and you're going to get 1.378. Okay, so we now have our parameter for mu and our parameter for standard deviation. What's the last condition we have to prove? We have random, independence by the 10% condition, and now we have to prove approximately normal. Okay, and in order to prove approximately normal, we're using either the assumption if they're less than 30 or the central limit theorem if they're greater than 30. So our samples less than 30 or greater than 30? Greater. So we would say 80 is greater than or equal to 30. And 100 is greater than or equal to 30. So by the central limit theorem, we assume approximately normal. Yes?
Like in FRQ, do we have to write out central limit theory if we do CLT?
You can write CLT. Even on the AP exam, they'll accept CLT. So now we met all our conditions. So we're done with the second C. So what's the third C? Calculate. And this is where we're going to use Desmos. And since we're using Desmos, are we going to have to convert to the z-score? No, remember the z-score is only if we have access to the standard normal distribution. But Desmos allows us to look at all the normal distributions according to mu and sigma. So we just need our information from our first C, which was communicate. And that was that we're finding the probability that mu of XA bar minus XB bar is greater than 4, where mu of XA bar minus XB bar follows a normal distribution, okay, of mu equal to 3 and sigma equal to what? 1.378. So we took the information that we got from the conditions, from the random and from the independent, in order to write our mu and sigma for the normal distribution of the difference in sample means. Once we have this, we don't need to do anything else. We don't have to graph the diagram or anything. We're going to go straight to Desmos. Okay. Change this. Open up Desmos. There we go. Okay. On Desmos, we're going to go to the plus sign. We're going to go to inference. Click on probability distribution. And on the normal distribution, we are going to put the values that we chose over here. Okay, the mu equal to 3 and sigma equal to 1.378. Then hit create distribution. Okay, and then from the drop down, we are trying to find greater than 4. So which region are we using? Right, and then we're going to type in 4. And we get what as the probability? Good, so we have the probability of mu XA bar minus XB bar greater than 4 is equal to 0.234. So once I have that answer, I don't need Desmos anymore. Okay, so I can get rid of this. Okay, and then I can go back here. And I can do my last C, which was what?
Connect.
Close, not connect. Conclude. Conclude or conclusion, either one. And that's where I'm going to write a what? A sentence. And I need to make sure I include context from the problem. So I'm going to say the probability that the difference in average scores between technique A and technique B is greater than 4 is about what percent? 23.4%.